Okay, so problem 3 is it's a little bit more complicated than problem 2, but I think it's actually you'll see that once you actually start going through this, it'll be a little tricky. You'll go through a little bit slowly, but you shouldn't actually find that you're doing too much work. I think you'll spend more time thinking about this problem than you will actually like spend writing things out. And so the main tricky part I think is this triangular load and dealing with this across this corner here. So I'm going to show you how to deal with the triangular load first. Let's pretend that we're looking at this problem. This is just an example for a triangular load. It's not your actual problem. But if I had this kind of load, my shear diagram, I'll try to draw these consistently in the same color. My shear diagram would look like a parabola. So I always tell people to follow their arrows. So in this case, I have a downward arrows, right? I've started off at 0 here because I have no forces acting here. I start off at 0. Downward arrow, so I know that my shear diagram is going to go downwards. And the value of my shear diagram, or the slope of my shear diagram, is the value of my distributed load. My distributed load is increasing in value. So the slope should be increasing, or the magnitude of the slope should be increasing. What that means is that I'm going to have a parabolic slope. So if I draw this, I'm going to get some shape that's like this. And if I had my vertical reaction up here, I need to end at 0. So at the end, my reaction is pointing upwards. Right, this is a cantilever, so the reaction is counteracting this triangular load. That reaction will take me all the way back up to 0. My moment diagram, so this is quadratic. My moment diagram is going to look something very similar. And I'm going to just draw positive up for now so we don't get confusion. The slope of my moment diagram is the value of my shear diagram. So I start off, I have a free end here, so my value is 0, and my slope is 0 initially because my shear is 0. My shear diagram is below the axis, so this is going to be, I'm going to have a negative moment diagram. And it's increasing faster and faster. So I'm actually going to have a cubic moment diagram. It's very hard to distinguish a cubic and a quadratic diagram, so just label that this is cubic. You need to specify, if you're doing this for an actual problem, you need to specify that the maximum value, and wherever crosses the axis, but for this example, I think that is enough. As I mentioned before, your axial forces and your shear forces are going to be related to each other. So if you look at this member, for example, the reaction here is pointing upwards. So this reaction is going to cause a change in my shear at B. When I'm drawing this diagram up here, when I'm drawing the shear diagram from A to B to C, I'm going to have a parabola, a jump, and then a decrease due to this rectangular load. So there's going to be a jump in my shear diagram at B in the horizontal member due to my reaction at D. I think that as I'm saying that probably sounds quite confusing. Just think about it for a sec, and it should make a little bit more sense. Like this reaction at D is like applying a vertical force at B. Okay, so with that said, for this problem, I recommend that you work from the outside in. At B, there's a lot of complicated things that are happening. Well, not complicated, but there's a lot of little things that are happening at B that make it difficult to work with. So like I was saying before, you're going to have jumps in your shear diagram at B, you're going to have jumps in your moment diagram at B, and I'd rather not deal with those. So what I like to do is I like to work from A to B, from C to B, from D to B, and then put all the diagrams together and then see what happens. So what do I mean by that? I mean like literally work with 3 separate problems. So for example, pretend that your first problem is dealing with this. Right, this is A, and you have B out here somewhere. So you cut it from A to B somewhere, and you're dealing with this force. The shear and moment diagram is at this force. Likewise, from C to B, or some rectangular load like this. X prime to denote that we have different x's here. And I'm going to look at this diagram separately. So I'm going to look at it from here to here, from C to B, and then I'll look at the one down below. So this one, you can almost rotate your paper and then pretend like you're solving this problem. X double prime. That should be that's probably the easiest way to solve it. So when you're drawing your diagrams again, so you're going to get 3 diagrams, right? You're going to get a diagram from A to B. You're going to get a diagram from B to C. So this is A to B. And you're going to get some diagram that's from D to B. You're going to take those individual diagrams and you're going to plot them all on the same sheet. So you're going to redraw your frame. You're going to put this diagram here. We're going to put this diagram here, and you'll put the last diagram here. A lot of people were confused about the sign conventions. They were concerned that, like, well, does it matter if I look at sign, for example, for the vertical members, the confusion was, does it matter if I look at sign from the left or from the right? So for example, from the vertical member here, if I look at it this way, let me redraw that here. If I look at it this way, my positive sign convention is this way, right? If I flip this around, my positive sign convention like this, positive sign convention will be this way. These two are not in the same direction, but it's okay, right? When I say it's okay, I mean that if I do it this way, I might get like I might get some value m here. If I do it this way, I might get some value negative m. So even though these arrows are pointing in opposite directions, the signs of these two values will be different. So you'll still have the same moment at the end. It'll still represent the same exact thing. So don't worry about which way you draw your signs. In the end, it'll all balance out because you'll still get that same, you'll still get your positive or your negative value. It'll correspond to 1. If you draw your sign this way, you'll get 1 value. If you draw it the opposite way, you'll get negative, but of the same magnitude. Okay, so I think that's everything for that problem. Just again, when it says it's rigid here at B, he doesn't mean that it's fixed. What he means is that the angle at B does not change. So this is like what I was saying for problem 2. When I'm at B, when I say that this is rigid, I don't mean that this is not equal to fixed. What it means is that my angle will always be 90 degrees here. So this might rotate, right? It might rotate some weird way like this. It might translate. This might end up, like I might end up out here somewhere. But the angle will always be 90 degrees at that point. So I hope that alleviates some confusion. Let us know if you have any other questions on this problem.